This conference will now be recorded.
Good afternoon, everybody, and welcome to this session of Mirabilis Design's webinar on assembling automotive electrical engineering networks. I'm your host, Deepak Shankar, and I'm the founder of Mirabilis Design. For the next hour, I will be talking about how VisualSim is utilized to create a completely new system design and system engineering methodology for the automotive sector. We're going to go through a lot of information during the session, and as I mentioned, there's a chat window where you can ask any questions. The session is going to start off with a quick introduction to architecture exploration and its fit in model-based systems engineering. We're looking at two examples, braking and electric vehicle with autonomous driving. And then we're going to look at what are the requirements for different types of users within the automotive industry, then look at some examples, and finally wrap up with a little bit about Mirabilis Design itself. Now, as a result of the volume of information, we're not putting all the information in one webinar. We split the webinar into three sections. Today, we're going to focus on the network and semiconductor overview. Next week is going to be on software, hardware partitioning, and for power performance trade-off. And then finally, on June 17th, we're going to look at ISO 26262 compliance and how the model can help you get early feedback for certification. First, we're going to start off with architecture exploration. This is a new topic, so I want to explain how this fits into the model-based systems engineering methodology. If you look at the current approach, there are really two mechanisms that are offered. One is you have a method to check the functional and mathematics and the algorithm correctness. Is my control theory working correctly? Is my signal processing correct? Then what happens is there is a requirements and a project management system where all the tests, the software, the connectivity to Simulink models or XML models are all maintained. What this whole system is missing is an early visibility into the entire design. If I'm putting an entire car or I'm putting a braking system, I want to be able to know all the details associated with the entire vehicle. And that portion is really missing within this particular current methodology. So what are we proposing? We're proposing a new layer over and above the map and project management. This becomes a virtual prototyping where you can incorporate the network, can be CAN, CAN-FD, FlexRay, Ethernet, MOS, LIN, but also all the wireless entities. And of course, adding your ECU, the semiconductor, software, integrating all of those. What is the purpose of doing this? Really the purpose, and I'll be talking about some examples a little later, is really be able to do trade-off analysis very, very early in the design process by utilizing detailed knowledge of your system operation. This is the major advantage of having this layer over and above your current methodology. Early trade-offs with detailed knowledge of your system. Now, if you look at the traditional approach would involve creating a model of the control theory, say in this case the drivetrain, the throttle valve. And what would you do with such a model? With such a model, you would pick up and you would have something like this where you have some inputs, the drivetrain, and you'd see the phi value. So you'd see the phi value and you'd see what the results are associated with phi value. And if I look inside of this, you will see the the state machine, and inside of the state machine, you will see the block diagram of my particular system. So this would be a very typical starting point for most architecture or most automotive designs. What we're proposing is that this is a good approach, but it happens much later in the design. something that looks like this, which is I've got all my wheel sensors, my engine gyros, and then I've got, like in this case, it's a FlexRay network where it can be an Ethernet CAN or any other technology. You have the whole network connected to an external ECU. And what happens is these are sending information to the ECU. There's a variety of statistics that I can modify, and it outputs a certain set of information. So what is the output? Shows me the angle, which is what is my gyro angle, and it shows me what's the utilization of the ECU. And this, as the angle changes, as my gyro changes, it shows me how much of what's the response time. So as you can see, as the angle increases, the response time also increases. So you can do a trade-off between looking at different aspects that are going to impact the system, like I can add like a proximity sensor or a road condition sensor and incorporate that with my gyro activity, or show a higher RPM and look at how much time it takes for the anti-roll response. So you're really looking at an end-to-end design. You're not just looking at how does that particular algorithm behave. You're looking at the overall system, and of course you can incorporate, as you can see here, the angle, the drivetrain, the power. You can incorporate all that control signal processing and other mathematics into the same system. Now, as I mentioned earlier, with your control systems based model, you're really looking at the correctness of your mathematics. What should be the coefficients? What should be the integration? What are the nonlinear aspects? When you're looking at system architecture embedded into model-based systems engineering, you're looking at a completely different analysis. What are you looking at? Things like response time. How many megabytes or gigabytes per second am I getting across my gateway or my Ethernet? What is the power consumed by, say, my semiconductor or by a braking system? What is the heat generated at the battery? What about the functional correctness? I have a software application. What is the functional correctness of the software application? Other aspects, I want to look at what is my ECU efficiency. What is the size of the battery that I required for an electric vehicle with autonomous driving? Also, this is not just about electronics. It's also about the mechanical systems, the thermal system. How do you provide early feedback on heat and temperature? So it's really about understanding what is the response time. Because if I use a lower processor, or I use a lesser number of sensors, or I use a smaller battery, of course my heat and thermal will be lower, but my response time will also be lower. Now all of these lead to the failure analysis and functional specification, because if I had all of this information now, that is while I'm starting to build the product, I can use this for early feedback for certification. That way I can figure out how I'm going to be running my system before I start the actual development. Of course, there are other things you can also be looking, like integrating 5G for your V2X and V2V analysis. So it provides an overall visibility into my design. Now, always the question is, yeah, I could do it later, but why deploy this new approach? A number of reasons. The biggest ones are, I want to gain visibility into my overall system operation before I find an error when I'm trying to build a product. I want to be able to understand what is the constraint for each signal or frame, and what elements go in hardware, what elements can go in software. Or for example, what are the aspects of Ethernet, say my control data timing? Do I really need it, or can I go with just Class A, Class B audio-video bridging? And of course, I want to have a single collaborative platform for the OEM, the Tier 1, and the semiconductor supplier. How do I bring all of them together into one single environment to work together? And of course, you have the technical details, which is identifying bottlenecks, identifying limitations, looking at reusable capability of existing technology, things like this. Now that you understood how architecture exploration with VisualSim fits into the model-based systems engineering, let's do an introduction to system modeling. As I've mentioned, we do have the ability to answer questions immediately. We have a number of application engineers working by. So I would highly recommend that you type in your questions as and when you get. I'm going to give it a quick break of about 10 seconds so people can ask any questions and answer. We can be happy to answer any questions. Okay, I think there are some questions coming along, but I'll go ahead and continue the presentation. If you look at system architecture modeling, there are really two aspects. There's the network and there's the hardware software that's connected to the mechanical systems. Now, let's start with the network. So what you have is you have an ECU which can run certain applications, have certain sensors connected to it. But what you need is predictability in the response time. So when my sensors bring in the data, when the user or the man-machine interface occurs, I should be able to respond within a period of time. Say braking has to respond within 35 milliseconds as an example. Now, all of these can be connected to a variety of networks, can be CAN, Ethernet, can be any of these subsystems. Now, within them, there is a variety of, like you can have 11-bit, 29-bit. Some can be FD, some can be regular CAN. You can have, like temporary errors, permanent failures. You can have different types of frames. All of those need to be integrated into this design. And of course, all of them go into a gateway. When you have gateways, you have a variety of scheduling technology. You have the traditional Ethernet priority, but you also have like Class A, Class B of audio video bridging. You have TSN, and of course, there are other standards also that are evolving that can become part of it. Now, what is the biggest thing on the gateway? I have too much of buffering, and I cause data losses. That's what I'm trying to protect. Now, this is a simple block diagram showing me here what I have is I've got one CAN network connected to a gateway with another CAN, and I have an Ethernet subsystem right over here. What do? I can generate a variety of statistics. For example, this shows me the statistics for different, the latency for different types of frames. So I have the CDT of TSN, audio video bridging, and the best effort of Ethernet. This shows me the instantaneous power over time for that entire system, not just a portion of the system, but the entire system. Plus, you can see the blue lines kind of hidden here that shows me what the average power over time is. This shows me which the ECU within the CAN is outputting or is wins the arbitration. So I get a lot of debugging information. Plus, I can see how busy different ECU are within my system. From here, I'm going to go into VisualSim, so we can start with a simple model. So this one here is every block in this tool or this model is taken out of here. For example, we're taking this out of the CAN library. You can have time-triggered Ethernet. You can have the TSN. You can have wireless sensors. So it's a variety of technology around the network that you can capture and utilize. So, for example, on the CAN bus, you can see, for example, this is the FD related information, but you can also get what's the speed. This is the signal dB. So for people that are familiar with CAN dB, This follows the CAN-DB format. You have the message format, the filtering, and you also have the power related for each one of them. Plus, we also have other information related to scanning, the random bit stuffing, and also what type you want, whether you want 11, 29, or both 11 and 29 format. So all of these are integrated into the library right here. So as a user, I can either just enter all my signals right over here, or I can disable it, where I can set this to false and have traffic generators feed in data into one of these nodes over here. Now, extension to the model, I can also introduce errors. I can randomize certain information. Plus, I can also have other types of information in the system that I can model. For example, here, sorry. Here I have, like, what are the classes, the what are the traffic streams, the priorities. All of that information is captured right over here. Now, this particular model that is actually is on our LinkedIn page and also on YouTube. So for those that are interested, can download and view this particular step-by-step on how to construct such a model. Now I can go ahead, all of these have predefined statistics. So what I can do is I can go ahead and click on Go. And as you saw earlier, a variety of statistics are generated as part of the model. Now, let me just go into this one for a second. As you can see here, the CDT is always good, which is at this level. You can see the class A and B right over here, but you see these spikes. So this tells me there's a credit problem right over here for this particular gateway that is not being addressed and needs to be taken care of. So using this right up front, I can figure out what is going on in my system. So another thing, for example, over here is the power. For example, notice over here, I have a few spikes. Now, if you look at this, you can actually see I've got 1, 2, 3 ECUs that are turned on at the same time. They extend for a certain period of time, one of them falls, but then another one starts up. So you can see that that aspect of where I have all ECUs running at the same time can cause an overload on my battery and my power supply system. So these are things that you can get early feedback before you start your development. So this is the parameter that we were showing you earlier right now. Now, one of the things you can do is you can scale that model where you only saw the braking system to integrate the entire vehicle. So here, it's no longer, or I'm sorry, a simple model with 2 ECUs. Now we actually have a system with about, we got 4 ECU networks, but 1, 2, 3, 4, 5, 6 Ethernet networks, and then we have 1, 2, 3, 4 gateways. So now we're expanded beyond just two simple CANs to now having a full automotive network where you can integrate all the different aspects. So be it chassis, braking, body, infotainment, everything can be integrated into this one single model. So to go ahead and look at that particular design. So this one is here what you're seeing. So you can see, for example, this is one of the Ethernet nodes. So you can see the traffic, the number of CPUs, what kind of protocol we're using, TCP, UDP, task size. So it's not just Ethernet, but if I go to this block over here, again, all of these are now what I call hierarchical blocks. When I click here, you can see the lower level details of what's happening within that block. So that way you can connect them up to the overall network right over here. And of course, associated with every system, you have a variety of statistics, or I'm sorry, a variety of databases that you need to configure. Some you can leave default, some you can configure to whatever you require. For example, when I run the simulation, notice the earlier ones we only had like 2 or 3 statistics that we generated, but now it's no longer just like 2 or 3, but we now have a lot of communication. So data and sensor data from a variety of subsystems are going right across the network. So now you can actually see the power is no longer just one node or one network. It's the power across the entire system. But you can see node 4 goes to 5, 6, 7, or for example, 5 goes to 1, 2, 3. So you can see the statistics for each of the individual subsystems. You can see all the activity on my CAN. So we haven't generated statistics for all because that would just clutter up the screen too much. Just certain ones that you can then see and try to understand what is happening in this particular design. But as you can see, even with a whole network, you can generate a variety of statistics for my particular design or for my particular architecture. So you scale from something that is just a single braking system to something that has the entire automotive network. Now, you saw the whole network. You saw how the whole network was constructed. You saw traffic. You saw how you can create the signals in the frames. Saw the gateways, configuring of the routing. All of those can be set up. Now, let's quickly talk about how do we create the ECU, which is the hardware and software in my system. ECU with 2 processors, a DSP I/O, and some bridges. Now, there are 2 parts to defining the ECU. The first part is the actual hardware platform. As you can see, we got 3 processors, I/Os, and bridges and buses. But we also have the application, which is a series of tasks with transfers between the tasks. And we have a variety of traffic, so variable input streams that trigger these particular applications. Some of them can be periodic, some of them can be based on interrupts, or some of them can be based on the driver activity or someone else with, like, say, a remote in the car for air conditioning. Now, how do we map this into a real vehicle? The way the mapping works is you build a hardware platform, you build the traffic sources, which are what we call the workloads, and then of course you define what is the sequence of events that occur. So you have the I/O, CPU, DSP, but you also have the transfer between them. They're also defined. So the advantage of this approach of having a behavior architecture is that you can change the architecture, keep the behavior, or you can change the behavior, keep the architecture. Or you can add additional behaviors or additional applications. Same model can be reused across your design platform. So for example, if you decide that I'm going to have this one ECU format that I'm going to use over the entire car, so all the 150 ECUs are going to use this one platform. So then what I can do, since all of these are fully configured for parameters, you can, for each one, you can try different types of behaviors and see what the performance is for each scenario. So what it allows you to do is allows you to create a platform where, one, you can have your hardware software analysis on each ECU, plus you can use this for communicating with the semiconductor teams in your, either within your organization or outside. Now, the other aspect is the libraries. These form the basic essence of how to construct the models, because we don't want to spending a lot of time trying to recreate different components. So we provide all of them in the library. You drag and drop them at each of these individual components, and you get your system model. Now, again, statistics. Why do you need to analyze your ECU before you go commit to saying this application is going to run on this ECU? The reason is impacts of different parts of the system. So for example, if I like speed up the bus, how does the latency for my task 1 and task 2 change? If I put in a slower processor, or I move from, say, a microcontroller to a low-end microprocessor, what is my performance difference? So I'd like to look at all of those before I actually commit to saying, yeah, I'm going to do this. So this is what allows you to experiment with the network and the ECU. Now going forward, I'm going to show you how you can integrate both of those into one system model. Now, let's look a little bit about the challenges and what are the libraries we provide for the automotive network. Now, I'm going to stop here, take a quick break, so in case anybody has any questions, I'd like to have them go ahead and ask those questions through the chat windows. That way, you would be, we would immediately answer those questions. Okay, I'm going to move forward and continue the presentation. So, VisualSim has a large set of libraries. As you can see, we have a huge coverage of libraries. Now, not all of it is required by you, and different parts of your organization may use a different set of libraries. For example, the networking group might use the Ethernet, the audio-video bridging, the 5G, and the FlexRay. But then the software group might decide to use the AUTOSAR. And of course, the hardware or the ECU group might decide to use the AMBA bus or might use the processors. So there's a variety of technologies that can be used across the organization. But VisualSim provides the complete coverage. Now, let's look at different levels. You got the system level, which is looking at the overall vehicle. You have the hardware software level, and then you have the system integration level. At the systems engineering level, you're really looking at how do I tie in the network with all the mechanical systems. So this is, I've got my drivetrain, I've got my power system, I have the wheels, I have the engines, I have the gyros, I have the accelerometers, I have all of those. How do I tie that in with the electronics and with the networks? And I have to capture behavioral requirements like battery capacity. What is the maximum thermal representations? What is the response time? What's the throughput? Then I have the hardware software where I'm really experimenting with different mapping strategies. What happens if I implement this in hardware versus I implement this in software? Or, for example, can I implement the whole system in software without, investing in a new ASIC, so I can, save my development cost, get to market faster? Or the other question is, how many signals can I put into a single ECU? Some of them may be analog, some of them may be digital, some of them may be large-size data like videos, some of them may have a lot of processing like LiDARs. So how do I combine them into a single ECU? Of course, the biggest challenge in any of these designs is related to deadlocks. How do I avoid deadlocks that where I'm trying to run something and my software can't run the system because the ECU does not have resources to run it, or certain tasks that have to be completed are required for this particular software to run and they're not available. Now that you look at the network, how do you look to connect the electromechanical, how do you look at the software? What you really are looking at is how do I integrate an application into this thing? So I already have a car system. Now I want to put autonomous driving into it. I already have it. Now I want to put V2V into it. How does that work? How can I integrate at a system level to put all of these things, all of these different designs together? Now, we're going to take a look at the braking system in a little more detail and try to understand how we integrate the sensors, the network, and the ECU into a single model. So what you see over here is something that looks like a car. So I got the wheels, the four wheels, the front and back. I have the brake pedal, there's a gyro in the middle, and a proximity sensor, the engine, and the road conditions. So what I have over here is all of these initially are the sensors. They're sending in different types of information that's being sent to the brake ECU. The brake ECU is doing processing and storing data, but then when either the proximity sensor or the brake pedal, so proximity sensor is where you notices you're too close to a vehicle in the front or side. The brake is where the user applies the pressure on the brake pedal. That happens, the brake ECU starts processing that data and looks at all the others. For example, what's my angle, what's my engine RPM, it looks at other aspects like, for example, the road condition, and then determines how much of power should or how much of pressure should I tell the wheels to apply, and it sends that across the network to all the different wheels. So this is, in a sense, the entire braking system of the vehicle. Now remember, it's only a part of the entire automotive EE. As we saw, this would become part of a larger system. Now, getting into the ECU itself, so I have the interface to CAN, and what I have here is I've got a DMA, I've got the Cortex, this is the ARM Cortex A53, with the buses, the L2 cache, AXI bus going out to an external memory, which is the DDR. So this is the ECU board that I've created for this particular braking system. Now, what are the types of analysis you want to generate? You want to look at the voltage discharge. Now, this is 10 to the power 2, so it's not 0.4, but actually 40 volts. And you can see at the same time what's my charge curve, what is the value of my charge curve. But you can also look at the braking latency. This is associated with how to, time taken to get to each of the wheels. That's the heat display in joules over time, the average power and the instantaneous power of my system. Plus here, whether I've read the correct data or whether I've read the incorrect data. So this is data coming in from the different wheel sensors. I'm checking to see at each time interval and for different wheels whether the data was read incorrectly or the data arrived either corrupt or it arrived too late. So it missed the timing deadline. So it reports that information as well. So now I'm going to go over to VisualSim. So this is the VisualSim model. As you can see, I've got the wheels, I've got the engines, the proximity sensor, the ECUs. So you can see this is my gateway. So it's got all the information related to the gateway. I have all the things like, for example, this is my classification table. So it shows me gateway to CAN 1, his ID goes to wheel 1. Or for example, I can do an identity map, which is CAN ID to Ether ID mapping. Or I can look at the software scheduling and say task 1 goes to ECU 1 versus ECU 2, and that's the priority. Also, I can have other aspects such as the bridge. In this case, I'm just doing a broadcast. I'm not restricting it to say go to one destination net or go to another destination net. I'm saying just go to all of them. So it's actually all sensors are sending data to all the ECU nodes. And of course, you can have the routing table. This shows me like from source to destination, what was the distance, the speed, and whether it's a bidirectional system. And of course, I can go into the ECU as a variety of data, like for example, which processor was the clock speed. Go in, you can see the entire system over here. Now, this one here, just like my network and my gateway are extremely accurate, so is my hardware platform. So for example, by going here, you can see the ARM Cortex implementation right over here with an instruction stream being fed into to run the system. Similarly, if I look at the AXI bus, that's something that the semiconductor people would associate with and understand how the system would behave. Similarly, like I can have memories, so I can have whatever type of memory I want, DDR1, DDR2, DDR3, DDR4, and even supporting all the way up to DDR5 as well. So we have all the different variations also with the system. So what do we have now? detailed network, detailed sensors, detailed ECUs. I'm going to go ahead and run this. So not only are the statistics that I showed you earlier being generated, but there's also a variety of other statistics that are also being generated right over here. So you can see, for example, at different times, what's the speed that the vehicle is running at. So that's my engine RPM translation. Shows me over time what's my brake latencies. Here it shows me what is the state of the road. What is the actual road state, but also, what is the actual value seen by the device. So it's not just, I have this particular, this particular road condition, but also is the sensor outputting the expected road condition and not some other value. So, and then of course you can also get other types of statistics, like for example here, I can get specifics on the channels, on the ECU, all of that type of information as well. Also notice I'm running this for 1 second, and the whole model just took me about 58 seconds to run. So 1 second of the entire network for the ECUs took only about 58 seconds to run. Less than a minute. Now let's look at another application. So we saw braking. Now we're going to look at another application. In this case is the electric vehicle. So you can see there's the battery subsystem. You can see that's the ECU network. So I've got my engine, body, ADAS, all of those here. These are the different local functions within each of the engines, and that's the power system. Here, for example, and we're going to talk about this in a lot more detail next week during our hardware-software mapping for autonomous driving. But here you can see how the system is behaving, when I assemble up the entire network. So now it wasn't just the automotive, but now we're moving over to something a lot more, which is the ECUs and the the sensors that are looking at more extensive processing. So it's not just looking at a single value of braking and temperature and the proximity and the road condition and the engine RPM, but rather looking at picture data and videos and things like that to make decisions. So this one here is our thermal and battery subsystem. So you can see the from the motor you have the charging circuit. This one here is the discharge cycle, so you can see all the statistics. These here are computing different types of statistics, especially in terms of life cycle, heat, thermal effects, things that you can see right here. The thermal aspects are also captured. Now, looking at it from the network and hardware, let's also look at it from the software perspective. So now what I'm going to do is start off with AUTOSAR. So what we have over here is we've got 2 ECUs on the network. It's got task 1, 3, and this one's got task 2. And these are the runnables that are associated with each one. What we're trying to do is we're trying to get all the sensors connected across the network, connected to this ECU, and we're looking at what's going to be the response time from this ECU. So in terms of when the task is ready, the time it takes to go to ready to run, and then of course actually executing of the data. So is there a huge difference in the latency between ready to run and actually executing? So this one here shows you the internal. So that's the ECU node, which is the the AUTOSAR details. So you can see the runtime environment. That's the runtime buffer. The OS, the scheduler, the watchdogs, the communication input connected to the Ethernet. All of those aspects are modeled as part of the ECU. Now, this is the thing that is very interesting about this particular design. What we have here is 2 scenarios: without fault, which means you're not introducing any fault, versus we are introducing a fault into the system. Now, I'm not going to look at it here. I'm going to go into the model so we can actually look at the design. So what we have here is we've got 6 nodes on this network, and we have this particular node that's got the ECU that we're talking about. All the others have sensors and they have other types of activities. And we have the RTOS, the watchdogs, the ECU communication, RT, and then of course the runnable. So I'm going to go ahead and for a fixed configuration or for a fixed table of, so this is my data on the RT buffer. This is my list of tasks, and you saw those on the earlier system over there. And this is my list of endpoints right here. And of course, these are the checks for the deadlines between this checkpoint and this checkpoint versus the alive supervision to see which checkpoint, how long it's been running. Again, a lot more discussion on software is happening next week, where we're going to talk about all the profiling and all of that information as well. So when I go ahead and run it, a lot of information is coming, but I'm only going to focus on two aspects. This one right over here, which shows me the utilization of processor 1 and 2. So you can see processor 1 gets almost 95%, processor 2 gets to 85%. But you can see one of the things is processor 1, the buffering seems to be going up. So eventually, what's going to happen is it's going to actually run out of steam, and it's going to start losing data right over here. So we notice that the increase right over here is indicating one thing. The other aspect is this is my my ready to run, and that's my running, and that's my waiting. And you can see they're in a pretty flat format. What I'm going to do is I'm going to change this to false. Oops, I'm sorry. I inverted it. So this one, for example, is where I do not have any false in it. So you can see the ECU 2, processor 2 has about 80% utilization. Processor 1 has 20% utilization. But now, when I look at ready to run and running, there's a very small range. The latency is extremely small between them, which is like a very, very small value, which means there's almost like nothing waiting. As soon as you're ready to run, there's always a value, always an ECU available, and it starts executing. As opposed to the earlier one, where we had an error, and as a result of which you could see the ready to run was constantly going up because there just wasn't an ECU available as a result of the new scheduling table that was modified as a result of a fault being introduced. Now, of course, here you can see, the execution times at each of the ECUs. I can change this back again to true and rerun the simulation. And you can see how this ECU changes. And of course, you can see the ready to run. Look at the time that it's waiting keeps on increasing. And of course, we saw earlier the buffering also is increasing. So this is something that you can capture as part of your software analysis. Again, we're going to go into a lot more detail next week. Semiconductor. Now, I've introduced semiconductor here, but from the context of the network. Semiconductor from the context of the ECU and the hardware architecture will be covered in more detail next week. This is an Ethernet switch. This is the NXP Ethernet controller. You can see the 5 interfaces with all their scheduling and their the flow through the particular system with their shared resources like memories and things like that. The same thing has been captured as a model in VisualSim from the 5 going through the VLANs and of course transmitter back to the next level 5. And these are some of the shared resources that are also part of the system. So if you notice, yeah, this is only a single channel, but we had a multi-channel on the other one. But what is critical here to look at is the fact that the block diagram here resembles the same design right over here. Why is that significant? It's significant because of the fact that then I can add in details for each one, and when a user that is not familiar with VisualSim looks at it, they can understand exactly how the system has been constructed. Now, the Ethernet, a variety of parameters are set up. You can have a number of channels, so not just 1 or 2 or 4. Even though the NXP has only 5, you can have 20 channels, see what happens. You can have bits. You can have, like what's my XMII modes, the VLANs, the policying. All of that information is captured as part of the design right over here. Of course, you can see these are all the different value tables that need to be configured to get the Ethernet run. Now, completely a different set of statistics. So, for example, here you can see the latencies. So, one of the things you notice here is the red is always here, which is very, very important because the control data times should not have an alteration. They should happen exactly at the slots. Those are happening. But these spikes here are related to these, which are the credit policies for A and B. In this case, they're only sending out A traffic. So you can see what's happening. So these are all the good times, and these are where it's consuming a whole lot of credit. And it goes into negative mode. Because you can see what the Ethernet throughput is, and of course the buffer occupancy. So you can see for each of the channels, and for A, B, and control data, you can see exactly what the buffer occupancy is as well for the system. Now, that was on Ethernet controllers. Now, let's look at the ECU hardware, which is the processor. So you can describe a processor. In this case, you've got the ARM A77, the AXI buses, the networks, the memories, the controllers. All of those are captured as part of this particular design. What do we typically do with these kind of models? What we do is we look at the power and performance trade-off. So, for example, I have a requirement for the power to be within, say, 1 watt of power, but the number of frames to be processed has to be greater than 13,000. So, variety of analysis can be done. I can run all the tasks in software. I can move some of the tasks from software to hardware, and I can add power management to an existing design that I like very much. So, depending on what it is that I want to do, I might utilize a different type of methodology. Now, this is the model. As you can see, there's the power, the processor, accelerators, bus, memory controllers. And that, as you saw earlier, is the use case. In this case, it's an MPEG use case. So it's obviously something related to cameras and to autonomous driving. And you can see a variety of statistics. So this here shows me statistics related to the average power and it's compared to hardware versus software. And of course, like looking at the number of frames I was able to process, and who's consuming. I can look at which device is consuming how much power. So now, when I look at a model of this type, it looks completely different because this is the inside of the particular system. As you saw, the brake ECU. This is the inside of the brake ECU. Now, I can change parameters here to move some functionality from hardware to software. So, for example, when I run this, you can see here what the peak processing time is. For example, you can look at what was the average power, and you can look at also what's the amount of processing that is being done by the ECU on number of frames that have been processed. You see the power goes up to a maximum about 1.35 peak for instantaneous, while the average is below 1 watt of power. You can see the number of frames it processed. And what I can do is I can change this to say for the image rotate, which is this candidate over here, I'm going to move it rather than that on the hardware accelerator. Same design, but what I've done now is I've moved one of the functions from software into hardware. So now I'm going to see how that has impacted my particular design. Obviously, one apparent design is power consumption has gone up. As you can see here, this is the hardware accelerator, so you can see that that's been quite busy right over here. But what's critical is the number of frames, and I put on more than double Just by changing one, that if rotate frame to move from software to hardware, I've been able to double the processing, double the amount of processing that can be done just by doing that one movement from hardware to software. Unfortunately, it goes over my power budget, but what I can do is I can go into my power management system under my power cable, and notice here I capture the power for all the devices that are in my ECU. Same thing, going ahead and running it. Again, remember, we're going to talk about hardware software partitioning, about detailed hardware, detailed software next week. So please tune in next week for that detail. We're just going very briefly over it to give you a broad overview of the entire design. Also, the webinar is being recorded, so you can actually see the webinar. Afterwards, we'll be sending you a link to the recording as well. Now, here you notice earlier on it was sitting over here, it dropped to 0.2 and it just kept going up. Now you can see after it reached a certain period of time, it dropped to an idle state. So this can be used for doing more extensive power analysis of my system. Notice there's not much of an impact on my performance as well. So using this, I can actually do a variety of hardware software trade-offs for my ECU. Now, we did talk a little bit about fault injection into the particular system. Now, here we're going to talk a little bit about VisualSim fault failures. We're not going to go into a lot of detail because that's a whole 1 hour discussion. And we're going to keep that for 2 weeks from now on the 17th of June. We have another webinar where we will be capturing that information. But just to give you an idea, in this case, we're only looking at the faults related to hardware, but we have network faults, software faults, hardware, power system, the RTOS faults. So we've got a variety of faults that we're capturing. But in this case, we're just looking at the hardware faults, and this is the report that we generate from VisualSim related to failures. Okay. And again, just to remind you, as the session goes along, if you have any questions, go ahead and ask them, so that way, like our engineers could answer those questions. But you can always contact us later, and we'll be happy to answer any additional questions as well. Now, a quick introduction to Mirabilis Design and who we are. Company's been around since 2003. We are in a variety of market segments. We've won a variety of awards. We've got over 50 customers, and over 250 products have been built in VisualSim. And we've recently expanded to Europe and Asia, where earlier on we were primarily a US-based company, so we can actually provide a lot of local support in all those regions. Now, what does the Mirabilis Design provide? We have 3 things that we offer you. The VisualSim software, which is the tools you saw that I was using to demonstrate the different capabilities, and the libraries that go with that, the training, and the third one is services. We can build custom blocks, custom models, but also come in and do architecture analysis for you. So we can do all of those as well. Now, one of the questions comes up. You saw all the advantages from a technology standpoint. How does it help the project? One of the reasons it's very critical is either you don't do modeling or you do some very detailed modeling. VisualSim has the advantage of reducing the model construction time. So what can take 6 months can be dropped to about a month. Why is that important? The reason is you have more time to do analysis. When you do more analysis up front, you create higher quality products. And as a result of creating a higher quality product, you can do all your communication and refinement using this, using the model. As a result of that, you can identify bugs before they occur. So you can identify deadlocks, you can identify limitations. So your implementation time reduces substantially. As a result of which you can save 25 to 30% on your project time, but also increase the amount of revenue. With this, I'd like to wrap up our presentation on assembling automotive EE networks. I thank you all for attending this session and hope that you can attend the remaining 2 sessions that discuss the hardware software of the ECU and also functional safety. We'll be around for a few more minutes, so we can be happy to answer any additional questions you may have. Feel free to type them on the chat window.